So a golden rectangle is a specific kind of rectangle, and the property that it possesses is a rectangle that can be partitioned into a square. So you take the short side and you essentially square it off into a square and a smaller rectangle mathematically similar to the original. And so what that means is if you have a rectangle, and it usually looks something like this, if you square off on one of the short sides, and so what that means is you draw this in and you get a square, what ends up happening is the rectangle that is created, that's left over after you take the square, is similar to the original rectangle, which means, because the angles are all the same, because they're right angles, that the short side to the long side is the same in both of those rectangles. So we then like to take that golden rectangle and create what is called the golden ratio. And this golden ratio is what the really interesting part about this is. And we're going to talk through some different things that make this golden ratio interesting. So the first thing is we need to calculate it. So that we do that by saying the short side is 1 and the long side is going to be x. And then that means that x over 1, or just x, will be the golden ratio. It's the ratio of the two sides, the long side to short side, of a golden rectangle. The reason we can do that is because the way we created this partition is that we created a square, so we know that these sides are all 1, which means this length is x minus 1 and this length is 1. So the ratio of the two sides of the original rectangle is x over 1. The ratio of the long to the short of the new rectangle is 1 over, so this is the long side of the new rectangle, over x minus 1. This is a simple algebraic equation to solve. You just cross multiply, you get x squared minus x equals 1, or x squared minus x minus 1 equals 0. And so we then solve this quadratic using the quadratic formula, and we get x equals negative b, so the opposite of negative 1. So 1 plus or minus square root of b squared minus 4ac, b squared is negative 1, minus 4 times a, which is 1, times c, which is negative 1, all over 2 times 1. Well, the negative, because what the square root turns out to be square root of 5, because you get 1 minus a negative 4, or 1 plus 4, which is 5. Since square root of 5 is bigger than 1, we can't subtract because that would give us a negative value for x, but x is a length. So the golden ratio just turns out to be this: 1 plus the square root of 5 over 2. If you type that into your calculator, you can see what a relatively exact value of this is, and it's approximately 1.618 ... We'll talk more about what that is in a little bit. Okay, so the golden ratio shows up in a lot of different places. One way it shows up, and this applies to the similar triangles that we were just talking about, is in an isosceles triangle, a very specific isosceles triangle, and that is one that is, so it's an isosceles triangle, has a vertex angle of 36 and then base angles of 72. The reason why this is special is because that vertex angle is exactly half of one of those base angles. And the reason why that's significant is because if we bisect that angle, and so if I create an angle bisector here, then this angle becomes two 36-degree angles, which means this is 72. And what we just learned is that if two triangles have their angles the same, then they are similar. So this triangle that I created, this guy right here, is similar to the original triangle. And so hopefully you can kind of see how, oh, that's kind of like what we just did, except that it wasn't as clean as creating a square in a similar rectangle. But we're able, by using this angle bisector, to create a similar triangle inside that. And you could just keep repeating that process over and over and over again, like you can in the rectangle. So doing the same thing we did before, we let this side length be x and this be 1. And then the key thing to being able to see the golden ratio is to recognize, oh, wait a second, 72, 72, this triangle is isosceles. So this side is 1. 36 and 36, that triangle is isosceles. So this length is 1 from here to here. We call that point A to point B. But since this whole length is x, we know this is x minus 1. So we can say, okay, these are similar triangles because their angles are the same. So we can do one of the legs to the base. So x over 1 is equal to 1 over x minus 1. And that just gives us this exact same quadratic when we cross multiply, the exact same quadratic we got when we were looking at the golden rectangle. So you can think about this almost like a golden isosceles triangle. If I were to solve that, I would get that same 1 plus the square root of 5 over 2. Well, the reason why this is interesting and why one of the things that leads to the mystique around the golden ratio is because that triangle shows up in a pentagon. And so when we look at a pentagon, we know that one angle in a pentagon, and I'll do my best to freehand it here, is 108 degrees. And then what people over the years have done with a pentagon is they have created what's often referred to as a pentagram, which is the star formed by connecting the vertices or drawing in the 5 congruent, which is an interesting part about the pentagram. And a pentagon is that all the diagonals are congruent to each other. But you draw in those 5 things and you get this. And the reason why that's significant is because when we, we'll do another version of this. When we draw in just 2 of them, these 2 right here, what we end up with is 2 isosceles triangles on the outside with vertex angle 108, which means these 2 angles are 36. Which means the angles here turn out to be 72, 72, and 36. And so what's so interesting about that is in a pentagon, the ratio of one of the diagonals, all of which are the same, to a side length is also the golden ratio. And so that is a piece to it that is one of the reasons it has a mystique, because the pentagram is a symbol that's been used in lots of different things over the years, especially in ancient times and mystical type of things. And so the fact that the golden ratio shows up in there makes it even more interesting for those that love mathematics and mystical conspiracy kind of things along the way. So that we'll come back to the pentagon in just a second to talk about another nice use of that pentagon. But for now, I want to talk about how could I construct a golden rectangle? If I gave you a ruler and a compass, how might I construct a golden ratio? Well, to do that, we take a look at our number, 1 plus root 5 over 2, and we realize it's the same as this, 1/2 plus the square root of 5 over 2. Well, if we look at a square with side length 1, then if we take a midpoint of the side, we get 1/2. And so we know the golden rectangle is going to come some distance over here to create this similar rectangle. Well, we need the amount that we need to come over from this point to here. Remember, we did, if this is 1, then the golden ratio is just the length of that other side. So it must be square root of 5 over 2. Well, very conveniently, if you do find the hypotenuse of this triangle, connecting the midpoint with the opposite vertice there, 1/2 squared plus 1 squared equals this length here squared. This is just going to be 5/4 equals x squared. When we take the square root of both sides, we get the square root of 5 over 2. Well, what that allows us is to draw a circle with this as the radius to get this point right there. So I'm going to show you that really quickly on GeoGebra. And so we take a look at GeoGebra. We're going to create a square. And then in that square, we're going to take the midpoint of one of the sides. And so we're going to go the midpoint between A and B. That's E. And then we're going to take a circle and we're going to say we're going to create a circle with center E through point C. Well, what that tells us is a golden rectangle can be formed by looking at the intersection point between B, or between this line AB and that circle. And so that point is right here. This is the point that we're looking for. And so point G, and then we just complete the square, however you'd want to, the rectangle there. I'm going to make two perpendicular lines to do that. And so it looks like this. And so our golden rectangle is AD, this new point we're going to find right here, HG. That is a golden ratio. We can prove that. You can't see it really well on the screen, but I'll go ahead and type it. If I say, on GeoGebra, I can type in this input bar on the bottom, DH divided by HG, and that does equal 1.62, which is approximately 1.618, then rounded, correct? And so that is a golden rectangle. And actually what ends up happening is, the cool thing about golden rectangles is you can keep creating them inside themselves. They spiral down. And so I just create another square here. This new CHIJ is a golden rectangle. And then I can do it again, and I create a square here. And it is also, went the wrong direction. And so it is also going to create a golden rectangle. So CKLJ is a golden rectangle. And you can keep doing that process to infinity to create golden rectangles. Went the wrong direction again. And there's a spiral that's created called the golden spiral. And interestingly, it's not actually through the points, the vertices, but it's really close to that. You'd have to look into that a little bit to see how you find out what those points are. But this is the golden ratio. The other way you can construct it, I'm not going to do that on GeoGebra, but you can also take the pentagon. And it turns out that when you draw in these, the ratio of this length to this length is the golden ratio phi. This is called, that golden ratio is called phi. And so if you just create a rectangle off of it, where this is a square, you take this square, take a square off of that length, and then you complete the rectangle by doing a perpendicular off of that, that point. That is a golden rectangle as well. So you can use a pentagon, a regular pentagon, to create a golden rectangle as well. All right, then the last thing I wanted to talk about is I did want to talk about the Fibonacci sequence, and this is what Weihart talked about. Excel is a great way to explore the Fibonacci sequence. And so the way I do it is I put the first two terms of Fibonacci as 1 and 1. The third term is we're going to sum together the previous two. So we add together these two cells. It's A1 and A2. And then Excel is great. If you haven't played with Excel, there's so many cool things you can do in it. But one of these is if I just drag this down, it's going to repeat that formula, and it's going to create the Fibonacci sequence. And so you can see the Fibonacci sequence being made: 1, 1, 2, 3, 5, 8, 13, 21, 34, 55, 89, 140, and you can see all these terms. Well, what we learned is that in the Fibonacci sequence, if we take the ratio of the previous two terms, and so this one divided by this one, it eventually converges to the golden ratio. And so you can see the golden ratio being, 1.618033989. If you were to type into your calculator 1 plus the square root of 5/2, it would give you this value. And it's interesting how quickly it gets there, right? It starts to really get there by 377. You got 4 or 5 decimal places correct. And it just gets better and better and better as it goes along. It gets closer and closer to this 1.618. So that is the golden rectangle, golden ratio. Lots of interesting information about it. I hope you enjoyed learning about it. There's also, there's some really deep dives you can do. Feel free to do that on your own.